y, and they move at a velocity v1 and v2. And the idea is that particle m was initially at rest, meaning it had zero momentum and zero kinetic energy. Now, you cannot solve this problem with the level of knowledge you have right now in terms of energy. If you took some special relativity, you could, just by saying this does have, in fact, energy, potential energy, or rest energy is a better way of stating it, which is mc squared. That's where Einstein's famous equation E equals mc squared comes from. But without that knowledge, you can still solve this in terms of momentum, given the fact that you have mass, velocity, momentum here, so we can find everything in terms of momentum. So initially, the initial momentum, which means a big M right here, is equal to 0. And that's what we know. So this is going to be sort of similar to what you saw as a superelastic collision, where the potential energy, in this case rest energy is the proper term, gets converted to create a photon, a particle of light with energy and momentum, and two massive particles, M1 and M2. And here the term massive just means they possess mass, as opposed to a photon which possesses zero mass. So you might think, why does it have momentum? Well, you learn in physics too that the momentum of a photon is equal to its energy divided by the speed of light. And it has energy. So that's a famous conclusion from Einstein's theory of relativity. So you do not need momentum for that. That is the classical way of looking at momentum. But besides that, let me break things up first before we do anything else. This velocity vector here can be broken up into v2y and v2x. This velocity vector here can be broken up into v1x and v1y. So let me go back to initial momentum is 0 to state what this really means is the initial x and initial y momentums are both 0, because we're dealing with two dimensions. And since it's a vector, that means that the total, if this is conserved, momentum in both x must be equal to 0 after this particle decay. So with that in mind, let's look at P final y. There's only two things moving in the y direction, the component of v1 and v2. And we know how they equal, same way as before. v1x is v1 cosine theta, v1y is v1 sine theta, v2y is v2 sine phi, a different angle, and v2x is v2 cosine phi. So looking at this, the final y, which has to be equal to the initial y, is just going to be equal to, setting going upward positive, m1 v1y, which is v1 sine theta, minus the momentum in the y direction of mass 2, which is m2 v2y, which is v2 sine phi. And it's negative just because it's moving down, whereas m1 is moving up. And since this has to equal the initial momentum, this equals 0. My second equation is P final in the x. Well, everything going to the right is going to be positive. So that's the momentum of the photon, P sub gamma, minus both the components of the x momentum for m1 and m2 are the left, so they'll both be negative. So that's m1 v1x, which is v1 cosine theta, minus m2 v2x, which is v2 cosine phi. And what we want to do is find v1 and v2. Well, they're both negatives. Only the photon is going to the right, this is going to the left. So if you want to just have negative and distribute them, that would be fine. So we want to find v1 and v2. So the easiest way, oh, and also remember that this also is equal to 0, because this is equal to p initial x, because it was all equal to 0. So let's use the simplest equation, this first one. If I use that first one, I have m1 v1 sine theta is equal to m2 v2 sine phi. Now it depends how you want to solve it. You can solve in different ways. Let me give you one approach. I could solve for v1 by saying this is m2 divided by m1 sine phi divided by sine theta. I could just do that. You could solve for v2 here also.
You're using the y or the x?
Oh, sorry, times v2. So I solved for v1 in terms of v2. And all I did was divide both sides by n1 sine theta. That's all I did. Alternatively, you could have done it v2, but this is just one method. Now let's put this v1 into here. And if I do that, and let me now subtract both of these components here, because they're equal to 0, what I would get is, if I subtracted it, p gamma is going to be equal to m1 v1 cosine theta, so that's going to be m1 times m2 divided by m1 sine phi sine theta cosine theta times v2, because that's just putting in v1. Yep, that's putting in v1 into here, so m2 divided by m1, everything's there, plus m2 v2 cosine phi. So that's what I did there. All I did was then find v1, put in this equation, and solve for it like so. If I want to do this now, what I end up getting is p gamma is equal to, notice these m1s cancel each other out. So common terms I have is going to be m2 and v2. So m2, v2 are the common terms. And now it's going to be sine of phi divided by sine of theta cosine theta plus cosine phi. If I wanted to, which would help out the problem a lot in terms of this algebra, what I'm going to do right now is I'm going to multiply cosine phi, the second term in the bracket, by sine of theta divided by sine of theta, so that I have a common denominator. So if I do that by multiplying cosine phi by sine of theta over sine of theta, what I end up getting is p gamma is going to be equal to m2 v2 sine phi cosine theta plus sine theta cosine phi divided by the sine of theta. And I do this now just to state, v2 is now just going to be equivalent to the momentum of the photon times the sine of theta, and now divided by m2 sine phi cosine theta plus sine of theta cosine phi. I found v2. Finding v1 is much simpler now, because we already have an equation which relates them. We have that equation. v1 is equal to m2 divided by m1. Let me just write it there to remind you. Sine of phi divided by sine of theta v2. If I input v2 here, notice what's going to happen. I have a sine of theta in this denominator. I have a sine of theta in this numerator. They will both cancel each other out. I have m2 in this numerator. I have an m2 in this denominator. They will cancel each other out. So this will give me an answer that is the momentum of the photon, sine phi, divided by m1, sine phi, cosine theta, plus sine theta, cosine phi. And you can write in different ways if you wish to. Other trig functions, cotangents of phi and theta, that's fine if you wanted to. But this is just a way of relating them. And notice both of these, v1 and v2, The answers are solely given in terms of trig functions and the given angles, the masses, here m2, here m1, and the momentum of the photon, which is all that was given. What made this complicated was just that the angles were different, theta and phi. So basically everything you had to do for this was to say the initial momentum in both the x and y is 0. The final here in the y direction is the y component of the momentum for m1 minus the y component for m2. They also have to equal 0 since momentum is conserved. For the x, you had the photon going this way, which we'll just consider to be positive, and you had the two x components of the momentum for m1 and m2 going in the opposite way. So you had the momentum of the photon minus the two x components of m1 and m2. And that also was equal to 0, because initially they were equal to 0. So really this whole problem is basically this and this. Everything else is just algebra to try to solve it. But that is the whole physics of the problem, everything that's in black. The initial and final, and remembering that they are equal to each other. Which side? Here? Because notice the photon's going this way, and they're both going to the left. Momentum's a vector, so I just said this is positive and this is negative.